Welcome to Features of Core Instruction Part 2, Structuring the Mathematics Classroom. This is part of a series of modules created by the Rhode Island Intensive Mathematics Intervention Project. I'm Melinda Griffin from the American Institutes for Research, and I will be your guide during this session. So our goals for this session are to define what is meant by rigor in the mathematics classroom, to explore student and teacher actions related to the mathematical practices, and to understand the importance of growth mindset in mathematics. We will be focusing on Tier 1 instruction, that is, instruction that is provided in the general education classroom, received by all students, and that is focused on grade level standards, incorporating both content and practice standards. Our first section is on mathematical rigor. Rigor itself is a word that's tossed around a lot these days in education, but in the mathematics classroom, it has a specific definition. Let's take a look at why we talk about rigor and what it means in your math classroom. So why do we talk about rigor? Well, the Common Core Standards for Mathematics had three major shifts related to focus, coherence, and rigor. Focus refers to the content emphasized at a particular grade level. Coherence is how content builds across grade levels. It's important for mathematics instruction to be coherent so that students can make sense of the math and see how it's connected as they progress through grades. And rigor refers to the balance of math sense-making. We talked a little bit about focus and coherence in our Part 1 session when we looked at how the content and practice standards build across the grade levels. Rigor, on the other hand, is an area that has its foundation in the individual classroom. So let's take a look at these three areas, starting with focus. A good place to look when you're considering focus is in the introduction to each grade level in the Common Core Standards for Mathematics. This example from 4th grade gives a concise description of the main focus for this grade level, and it's followed by a more detailed description of each of these three critical areas. This does not mean that students don't learn anything else in 4th grade. Rather, it gives an idea of the main ideas that students need to master at this grade level. As we saw in Part 1, this chart shows a progression of math domains from grades K through 8. Coherence refers to how the mathematical topics build across the grade levels. For example, we can see in this chart that number and operations, fractions, begins in grade 3 and continues through grade 5. Within that time frame, students start with initial understandings of fractions as numbers. They move to seeing fractions as composed of unit fractions, and they'll eventually progress to operations with fractions, used mathematically and in real-world contexts. So that brings us to our third shift, rigor. Rigor does not mean just providing hard problems in the classroom. It should be a balance of three components. Rigor really refers to a balance of math sense-making to lead towards deeper mathematical understanding. If you look at the triangle here, you can see how the components of conceptual understanding, procedural fluency, and application, in other words, problem solving, are balanced to attain rigor. If we think about making sense of mathematical concepts, which we might also call conceptual understanding, this involves making sense of the math, being able to reason about it and understand math concepts and ideas. If we look at performing mathematical procedures fluently, we often call this procedural fluency. This includes knowing mathematical facts and being able to compute and do math. The last area, using mathematical concepts in problem-solving applications, often just called application, is applying what a student knows about mathematics in a contextual situation. A quality mathematics program makes sure to balance all three of these components together. So let's start with conceptual understanding. This is making sense of mathematical concepts, seeing the relationship between concepts, and being able to explain a concept. When we consider some helpful hints around this, consider that this is where you begin, but it may have happened in a previous grade. Conceptual understanding often builds across grade levels, so your students may have been introduced to concepts in an earlier grade, and now you are adding on to their knowledge. Think about it in terms of explaining the why and recognizing structure. Conceptual understanding really gets at why in mathematics, and this is critical for kids moving forward, as many of the properties and rules that they learn in elementary school, just using numbers, are going to continue to apply as they move on to algebra and variables later. We want to make sure we use multiple representations. It's important for kids to see these representations of concepts as they learn. In a later slide, we'll discuss moving from the concrete to the representational to abstract in more detail, but it bears mentioning here because parts are often skipped, and that leads to misconceptions. We also want to think about if students seem to be struggling with procedures, going back to check on their conceptual understanding of a topic will often reveal gaps or misconceptions. And while it can be tempting to just keep on pushing so that they attain procedural fluency, students will need that conceptual understanding as they move into later grades. So the next section of our rigor triangle was procedural fluency. This is knowing your facts, using algorithms, and computing accurately and efficiently. So some helpful hints for this. Please do not start here. Procedural fluency is a needed skill to be able to compute accurately and efficiently. However, it is not the be-all end-all of mathematical knowledge. Procedural fluency is definitely not where you should start when teaching a math topic. You want your students to understand the topic, not just know how to follow the procedural steps to get to an answer. Make sure you avoid overemphasis on procedures. While algorithms are an important part of mathematics, students should be able to explain why they work, and that comes from knowing the conceptual basis behind them. Be able to help your students move to more efficient procedures when they are ready. As students progress in their procedural fluency, they may become very comfortable with a particular procedure or algorithm. As the teacher, you might need to nudge them towards more efficient procedures once they are ready. Best practice in the mathematics classroom when moving from conceptual to procedural fluency is to use the CRA method. CRA stands for concrete, representational, and abstract. Students will begin their learning of a concept by using concrete objects, often called manipulatives, to explore the topic. They can move them around, rearrange them, whatever is needed to understand the process that's going on. The next step is to represent the concrete objects on paper by drawing a model or diagram to represent not only the objects, but the actions that occurred. From here, students progress to writing the actions symbolically, in other words, the abstract, by using typical mathematical notation. Let's take a look at a couple of examples. If we look on the left, a child may begin an exploration of addition by using base 10 blocks to represent numbers, which we see the girl doing in the picture. From here, she might draw a representation of the base 10 blocks on her paper, with the blue rods standing for tens and the green squares standing for ones. We will move from there to the abstract, which you see at the left part of the example. We see the addition problem written out using numbers and symbols. We do see each of the numbers decomposed into tens and ones, and that corresponds to the drawings at right. If you notice on the right, we see arrows and the words join and regroup, which showed the actions that were occurring with these. By providing all of these together on paper, the student can now connect the representational aspect, which goes back to the concrete manipulative she started with, to the abstract look of typical mathematical notation. A second example over here on the right shows a student working with one-step equations, using algetiles to model setting up the equation and solving it by making zero pairs. The student began the lesson by using colored squares on her desk, and then manipulated them to solve the equation. From there, she drew a visual model on paper that helped her see how subtracting 3 from each side of the equation kept it balanced and allowed for isolating the variable on one side of the equation to determine its value. In this case, we see the symbolic, in other words, the abstract, written along underneath each part of the diagram to show what's occurring mathematically and to help the student understand the main point of this concept, which is that you have to balance an equation by performing exactly the same operation on both sides. So let's look at some further considerations when we think about concrete, representational, and abstract. First off, help your students see the connections between each part of CRA. Otherwise, they may see each aspect as a separate concept. If the teacher doesn't make the link explicit between the manipulatives that they are using and a drawing of them, or how the drawing relates to the numbers and symbols it represents, then a student often sees these as completely separate concepts that they've learned. The move from representational to abstract is often the weakest link because it tends to be rushed, or because the lesson doesn't have enough time for students to progress all the way from concrete to abstract. So you want to make sure that when you move, you make that move explicit for your students. Also, don't move too fast. Students need time to move from one aspect to the next, particularly from representational to abstract. Teachers often spend plenty of time in the concrete, which is expected, as students are developing conceptual understanding and, due to the use of manipulatives, it may just take more time from a logistical standpoint. A lesson connecting concrete and representational is often provided in the course of a day. But to make the link from representational to abstract more secure, it can be helpful to briefly go back and model the concrete example for students, then show how to move to the representational. Once a few of these have been done together, then you can work on just the representational to abstract components, knowing that students have linked back to that concrete. If time is a factor, it's also possible to provide students with pre-printed or drawn representations and have them work from them as they move to the abstract. This should be done only after students have had the chance to create the representation themselves. It's also worth taking the time to show students how to represent the physical items. This will help develop some universality in their representations. In other words, a line means 10 and a dot means 1, a square means 100. And this will help you avoid kids getting bogged down in drawing things just so and precisely. Also remember that the abstract component can often be an algorithm. And regarding algorithms, this is where the shift is made from conceptual understanding to procedural fluency. The use of an algorithm, particularly the standard algorithm, should come last in the instructional sequence of a topic. So now let's take a look at the last part of our rigor triangle, application. This is taking what's been learned and applying it to a mathematical real-world situation. It could be solving non-rote problems, and it involves decontextualizing and contextualizing. Some helpful hints for the classroom here is do not save this until the end. You want to weave this in throughout your lessons. While students are learning about a topic, they need to see how that knowledge will be used. And this is also going to help them recognize problem types that are associated with a particular mathematical topic. In the past, teachers often shied away from word problems because they feared they would be too challenging for some of their struggling students. But we now know that providing a context often makes the math more accessible for children. Just because there are words does not mean it's an application problem. An application problem will have words to set the context, but there should also be a real need to reason and problem solve too. Some problems are just words inserted between numbers, with very little thinking required. You'll want to avoid using only keywords as a strategy. Keywords easily lead students down the wrong path, and this strategy often leads to misconceptions. You do want to use schema-based instruction. Application problems often fall into particular categories that all use the same approach or strategies to solve them. Schema-based instruction, also known as cognitive strategy instruction, can help students make sense of novel problems by recognizing the structure of them. So let's stop for a minute and think about the problem with word problems. Why are they so challenging for our students? As you see on this slide, multiple steps are required to solve problems, and each step offers up an opportunity to go astray and end up achieving an incorrect solution. Reading ability can also interfere with being able to access the mathematics at hand. And in addition, the cognitive load of solving application problems is high, and we know that students with mathematical difficulties and disabilities struggle more than their peers when they're solving word problems. It can be helpful for students as they work through problem solving to start to recognize different families or groups that problems belong to. This table shows some common operation situations for addition and subtraction and multiplication and division. Students can learn to recognize these groups as they gain experience in solving problems, particularly as they learn to read a problem to determine what is being asked, what is known, and developing a solution plan. Schema-based instruction makes use of these groups to help students organize their information and then use strategies to find a solution. So let's take a quick look at schema-based instruction. A schema is a way to organize or pattern information within a structured framework of known and unknown information. Rather than just focusing on keywords or a general solution method, such as identify, plan, solve, schema-based instruction looks at problem families and provides an organizational plan that's common to the family. This method has been found to be highly effective, particularly for struggling learners, because it gives students specific strategies for solving the problems. Problem schemas are determined to be either additive, as seen here on the left, or multiplicative, with multiple strategies available for setting up problems within these categories. Older students may combine both additive and multiplicative schemas to solve multi-step problems, such as those involving percent change or calculating a total price with tax or discount. Just because students approach a problem using the same schema does not mean that they will solve the problem the same way. For example, two students use a change schema to set up the problem. Emma had $9. Then she earned some more money doing her chores. Now Emma has $12. How much money did she earn? To solve the problem, one student adds on to 9 and gets to 12, and another student decides to subtract 9 from 12. Even though they use different operations, they both arrive at the correct answer of 3. Let's move on now to our next section, mathematical practices in the classroom. We've explored mathematical rigor some, so now let's see how these practices are an essential part of achieving the level of rigor required in the standards. So here are the 8 standards for mathematical practice that we discussed in the Part 1 video. We're going to look at how these translate to student and teacher actions in the classroom. So our first action is all students participate, not just the hand raisers. We know that equity requires participation, and all means all, boys and girls, English language learners, and students with disabilities. Explaining one's ideas and hearing the reactions of others is empowering and promotes learning. If students are allowed to remain silent, they may disengage and not see themselves as math learners. When all students are given the time and space to explain their thinking, students become learning resources for each other. There is no specific practice standard related to this action. In a sense, it relates to all of the practice standards, if students are given the opportunity and time to work on mathematics both individually and with each other. This is both a student and a teacher action, and it requires academic responsibility from both parties. So what can you do? Ensure that all your students participate in learning mathematics every day. You might need to examine your own personal biases to ensure that you're truly providing equal opportunity for all of your students. Don't assume that because a student is a special needs or English language learner that they can't do and learn mathematics. Be sure to watch for your own blind spots. Do you only call on kids you know will have the answer in order to keep things moving quickly? Do you tend to call on students from one side of the room over the others? How about only kids in the front? More often boys than girls? And do you call a student out by name and then ask a question? Any of these can decrease engagement with your students because they do not feel personally responsible for interacting with the mathematics. Also remember that silence does not mean that a student understands. Take the time to find out which of your students get it and which need some additional help from you. Our next action is say a second sentence to extend and explain your thinking. In other words, logic connects sentences. You need to justify. Brief single sentence statements are rarely enough for a viable argument. Students can go beyond and say another sentence to clarify their thinking, whether this happens spontaneously or if it's prompted by the teacher or another student. Even young students can learn to justify their reasoning to others. This relates to standards of mathematical practice 1, 2, 3, and 6. So what can you do to help students with this? Try posing purposeful questions. Powerful questions develop a deep level of understanding, and your goal is to help students add on and elaborate on their own thinking. You need to avoid asking just information gathering types of questions. Think about including questions that prompt students to think, such as, can you say more about? What did you mean by? Or how did you know? These types of questions can also be provided to students to use during group work, which fosters mathematical communication and preciseness of language. Also make sure that you ask intentional questions that make the mathematics more visible and accessible for students to examine and discuss. And probably most importantly of all is to make sure you give sufficient wait time so that students can formulate their own responses. Our next action is talk about each other's thinking, not just your own. In other words, understanding each other's reasoning develops reasoning proficiency. Students learn about mathematics by exploring their own and others' reasoning in problem-solving situations. Actively listening to peers increases the time focused on mathematical thinking and promotes cognitive flexibility. This student action touches on many of the practice standards. 1, 2, 3, and 6 are ones that are usually associated with communicating with mathematics, so it makes sense that as students work together and respond to each other's thinking, math communication skills will grow. S&P 7 and 8 are perhaps not as obvious. Both of these practice standards deal with patterns and repeated reasoning. Students often have much to learn from each other's thinking, and working together can help the mathematics emerge with greater clarity than by working alone. So what can you do in your classroom? Select tasks that allow students to decide which representations to use in making sense of their problems. Make sure you allocate substantial instructional time for students to use, discuss, and make connections among representations. Ask students to make math drawings or other visual supports to explain and justify their reasoning. And most importantly, help students connect their thinking to the mathematics at hand. You want to avoid just having show and tell without students making any mathematical sense. Our next action is revise your thinking. Revising explanations solidifies understanding. As students become more mathematically proficient and their reasoning improves, they should be able to identify flaws in their own and others' thinking. Revising work as a routine matter leads to better problem solving, and this also mirrors what we do as adult problem solvers. Just as a student might revise their written work in an English class to be clearer or more correct, they can do the same in mathematics. This relates to standards of mathematical practice 1, 2, 3, and 4. So what can you do to help? Help students realize that confusion and errors are a natural part of learning. Facilitating discussions on mistakes, misconceptions, and struggles helps students see that this is a natural part of problem solving. Offer praise for effort in making sense of mathematical ideas and for persevering through problems, providing students with specific feedback that helps them with revisions. Make sure you praise the work and not the child. Once again, providing and/or helping students create visual models of the mathematics is also going to help students think through problems. It will also decrease the formations of misconceptions. Our next action is use academic language. Academic language promotes precise thinking. Mathematically proficient students comprehend and produce mathematical representations that are embedded in ordinary and academic explanations and justifications, such as symbolic expressions, graphs, tables, number lines. Students use the mathematical words and phrases that are characteristic for their grade level, weaving them into sentences and paragraphs as they communicate with each other. Explicitly teaching math vocabulary is crucial for English language learners, and struggling learners too. Many times words have different meanings in life outside of mathematics, and you cannot assume that students will automatically pick up on these meanings during a conversation. Students need multiple opportunities to hear and interact with the language in order to make it their own. Using precise language can start very early on, as early as kindergarten. Explicitly teaching vocabulary is essential. Kids can understand the words equation, expression, and use them when they're explaining numbers. This use of precise language is key to avoid students creating misconceptions of their own. So what can you do to help? Consider using a Freyer model when introducing math terms in the classroom to promote student understanding. Freyer models are often used in other subject areas to learn vocabulary terms, and they're also quite useful in the mathematics classroom, where it can include drawings, pictures, and models to illustrate the word. A word wall is also helpful so that students can access the words as they need them in conversation. Most importantly, make sure you set a good example for your students by modeling the use of academic language when you speak about math. Our next action is to produce language, even if it's imperfect. We develop language through explanation. English learners may hesitate to speak in class precisely because their control of English is limited. However, practicing speaking allows them to become more proficient. Bridging the language barrier is important for ELLs to thrive in the type of classrooms that are promoted by our current mathematical standards. This also holds true for students with disabilities. Practicing speaking or communicating by whatever means is most appropriate for the student is critical to becoming proficient in using mathematical language to communicate their ideas. So what can you do to help? Educate yourself on best practices to help your English learners. There are lots of resources available online, including some self-paced learning modules. These strategies that you use for English language learners often work very well for other students in your classroom too. A great place that you can start is our own module called Effective Strategies to Support Language Development in Mathematics, which will go into more depth about strategies that you can use in the classroom with your students. Engage and persevere. In other words, productive struggle produces growth. This directly relates to the first practice standard. When faced with points of difficulty, challenge, or error, students continue to engage in the process and persevere. When students persist in making sense of a challenging problem and they try different strategies for solution, they're more likely to learn the mathematics than students who give up quickly or avoid challenge to the greatest extent possible. So how can you help? Learn about mindset and how it plays into whether or not a student will persevere. Help your students see that they are always adding to their mathematical thinking. And make sure to examine your own mindset as well. Growth mindset isn't just for kids. The website ucube.org is a great resource for growth mindset in mathematics. You'll find a link to it in our resource folder. This brings us to the last segment in our module, growth mindset, more than just a buzzword. This is a hot topic in education these days, and you hear the term growth mindset used liberally. So let's take a quick look at what this means in the mathematics classroom. Having a growth mindset in mathematics is an important part of building a mathematical mindset community. This type of classroom is open to all students so that everyone sees him or herself as a math person. This means that you, as the teacher, are also a math person. There are many resources related to growth mindset available. Dr. Carol Dweck pioneered this work at Stanford years ago and has since been joined by her colleague, Dr. Joe Bowler, who focuses specifically on mathematics. As stated before, the website ucube.org is a great resource for this work. I hope you've enjoyed this module, and I hope you'll also take a look at some of the resources that we have available to help you incorporate some of these ideas in your own classroom. Remember that you teach children first and mathematics second. And when it comes right down to it, math is not just about the numbers and symbols that we see on paper, but in understanding how we can use it to make sense of our own world. Thank you.